very, very happy to have with us Dr. Alan Icenhour this morning, who is Oak Ridge National Lab's Associate Lab Director for the Nuclear Science and Engineering Directorate. Dr. Icenhour is the person who operates the state-of-the-art nuclear facilities, in charge of that, and conducts technology research, development, and application programs that impact a large range of fields, from basic science to reactor development and to national security. The national security mission areas include R&D for both fission and fusion technologies, advanced modeling and simulation, stable and radioactive isotope R&D and production, R&D and development of technologies to address nuclear security issues globally, and safe and efficient operations in the nuclear facilities here. His experiences included a range of fuel cycle topics such as enrichment, radiochemical processing, stable and radioisotope production, nuclear fuels, radiation effects on materials, and radioactive waste management. Before joining ORNL, he served as a commissioned officer in the U.S. Navy on a nuclear submarine. After leaving active duty, he continued his service with the Navy as an active reservist, retiring in August 2010 at the rank of captain. He received his BS degree in nuclear engineering from North Carolina State University and his MS and PhD degrees in nuclear engineering from UT here in Knoxville. He is an adjunct professor of nuclear engineering at the University of Tennessee. He's a fellow of the American Nuclear Society and a member of the Institute for Nuclear Materials Management. Let's give a hand for Dr. Icenhour.
Thank you, John. I'll note, evidently you did a very good job staying on schedule yesterday, and now you're behind. I don't know if that's my fault or not. And the other thought I had, I'm sorry I was not able to attend any yesterday. I was in outer space of sorts. I was in Washington, D.C. So probably would have been better to be here. But this morning I've just got a few remarks I'd like to make because I met with John many months ago now, I guess. I don't remember the exact date, but we were talking about synergy and how do you bring together various technologies, ideas, capabilities in order to enable something bigger. And certainly at Oak Ridge, that's what we try to do. And I want to spend just a few minutes and talk a little bit about history. I like history because I think we can learn a lot from it. We can remember our capabilities, we can remember our mistakes. And then I'll talk a little bit about this theme of synergy and how we're trying to take advantage of it, and it's really in the context of what we're doing in the nuclear reactor space. So to start with kind of the history, and many of you probably already know this, probably know it better than I do. But throughout this year, we've been celebrating the 75th anniversary of the Oak Ridge National Laboratory. During that time, we've been able to showcase many of the science and technology achievements of the laboratory, which has also served as a reminder of our capabilities as a nation to rapidly innovate. On November the 4th, 2018, which is 11 days from now, if I did the math right. That date marks the 75th anniversary of a seminal event in the life of the laboratory, and indeed a seminal event in nuclear energy and more broadly for nuclear technology. It was at 5 a.m. on November the 4th, 1943, that the X10, which is now Oak Ridge National Laboratory, the X10 Graphite Reactor went critical. It was the world's first continuously operating nuclear reactor. It was built for isotope production to demonstrate gram quantity production of plutonium. That reactor, now an American Nuclear Society National Nuclear Historic Landmark, is just a few miles from here. And maybe some of you took the windshield tour this morning and saw it. That reactor was built in 9 months. Think about that, 9 months, a remarkable achievement. But it is even more remarkable when considering the context of this science and technology advancement. Chadwick discovered the neutron in 1932. Nuclear fission was discovered in late 1938. And CP1, Chicago Pile 1, demonstrated a self-sustained fission reaction on December the 2nd, 1942, a little over 11 months earlier. The X10 Graphite Reactor serves not only as a historical marker for the birth of Oak Ridge National Laboratory, but more importantly, it spawned new areas of science and technology that we benefit from today. We can trace those benefits to many areas, such as neutron science, with the first neutron scattering experiments being performed at the graphite reactor, and those experiments resulted in a Nobel Prize. Biology and environmental science for the understanding of the effects of radiation and radioactive materials on humans and the environment. Isotope production and research and development for industry, science, security, and medicine. And indeed, the first shipment of medical isotopes produced by the graphite reactor was made in 1946. There were materials development for extreme environments, radiochemistry and separation science, national security and nonproliferation to enable the peaceful use of this new nuclear technology. Modeling and simulation along with the measurement of nuclear data. And there was an education and training component that developed, such as the Oak Ridge School of Reactor Technology, ORSORT. This program was the forerunner of the Navy Nuclear Power Training Program, and it granted DOPE degrees, D-O-P-E. Does anybody know what that stands for? Doctor of Pile Engineering, DOPE. I would have been proud to be called a dope. And there are many other areas of science and technology advancement that can trace their heritage to the X10 Graphite Reactor. And that reactor and related efforts from the Manhattan Project established the foundations for the development and deployment of nuclear energy technologies. It's interesting to note that in 1948, a tiny steam engine was used to light a bulb using heat from the fission reactions in the graphite reactor. Very interesting because it wasn't an authorized experiment. But once that was demonstrated, everybody realized what they had, because this event illustrated a historic arc from discovery of a tiny particle, the neutron, to discovery of fission, to a man-made self-sustained chain reaction, to a continuously operating reactor, to ultimately showing how fission energy enabled by that tiny particle could be harnessed. These rapid achievements ignited innovations and applications for reactors beyond the graphite reactors. And indeed, 13 reactors have been built and operated by Oak Ridge National Laboratory to demonstrate different concepts, as well as enable scientific discovery and isotope research and development and production. Some of these concepts, such as molten salt, are re-emerging today. Following the Manhattan Project, reactor technology evolved from the state-of-the-art at the time, which was governed by the materials, manufacturing techniques, simulation capabilities, and sensors and controls that were available. Our nuclear navy and commercial nuclear fleet emerged from that state of the art, and so did our approaches to regulation. Today, thanks to many years of investment and research, we have a new state of the art. We have an opportunity for synergy. Technological advances in areas such as materials, advanced manufacturing, high-performance computing, and artificial intelligence can shape a new approach to reactor design, manufacturing, licensing, and operation. Together, such advances can enable reactors for which design constraints can be relaxed and increased complexity can be achieved because we can actually build it. More efficient regulatory approaches can be used because of the depth of understanding gained while building the reactor. Operational envelopes can be widened because we thoroughly have insights into real-time and predictive performance. A rapid innovation cycle is achievable because we can quickly demonstrate concepts. Flexible and scalable solutions can be deployed because the technology approaches can be rapidly adapted to new designs. And more autonomy is achievable because we can adapt approaches already being used. Recent advances in science and technology demonstrate that such an approach can be achieved. For example, a new cladding material, we call it FECRAL, iron, chrome, aluminum. It was developed and a lead test rod was inserted into a commercial reactor this year, in February of this year. And this was done in less than 7 years, defying the conventional wisdom that points to a 25-year development timeline. This effort used computational material science approaches to quickly establish the ideal composition, which was then combined with an extensive but focused testing campaign. The technology was then transferred to a commercial vendor, resulting in the lead test rod. Additive manufacturing techniques have been used to demonstrate a new methodology for producing control plates for the high-flux isotope reactor. These components have a very complicated fabrication process, and ultrasonic additive manufacturing demonstrated that a new way is possible. Ultrasonic and other advanced manufacturing techniques are now being extended and demonstrated for other reactor-related components. And I know you're going to have an in-depth talk about that from Bill Peter, and you'll see the exciting advances in that area. Integrated multiphysics, high-fidelity modeling and simulation. Wow, that's a mouthful. But it's demonstrating the capability to be both predictive and influential to operations and economics. The Consortium for Advanced Simulation of Light Water Reactors, or CASL, has many examples through its test stands that have accurately simulated many years of reactor operational cycles, including operational phenomena such as crud-induced power shift, and has also accurately simulated the first-time startup and power ascension of a reactor, Watts-Bar Unit 2, and it demonstrated that with unprecedented fidelity. Such capabilities can be applied throughout the evolution of reactor concepts, from design to manufacturing to licensing to deployment and operations. Finally, artificial intelligence methods combined with the availability of increased data streams from sensors can be used to provide real-time insights to reactor manufacture and operations. During manufacture, the pedigree of a component can be established, which enables the realization of concepts such as born qualified. Additionally, increased insights through more sensors and data during operations, combined with modeling and simulation capabilities, provide opportunities for increased autonomy. Bringing together today's state-of-the-art, that synergy, can help with accelerating deployment and address the economics of nuclear energy technologies, which is a theme you hit on in your question this morning. It is these advances that will help extend the remarkable arc of achievement we traced to 1932 by strengthening the foundation for development and deployment of nuclear technologies and energy systems. And it is that arc of achievement that helps remind us of our capability to rapidly innovate from seminal discoveries to applications. Thank you.